Greetings from the sub-ether. This is Alan with another extended color basic video following up to a previous installment where I discussed the different high-resolution graphics modes of the Radio Shack color computer. Let's recap that by looking at this wonderful text screen that you can barely see. There are P modes 0 through 4. P modes 0 and 1 are 128 by 196 with either 2 or 4 colors. P modes 2 and 3 are 128 by 192 in either 2 or 4 colors. And P mode 4 is our 256 by 192 with 2 colors. So those are the resolutions and the amount of colors. You either get 2 or 4 colors. As far as memory usage, well, P mode 0 is 128 by 96 with only 2 colors. It takes 1.5K because there is 1 pixel representing 1 bit is 1 pixel. Therefore, each byte, there are 8 pixels per byte. So 128 by 196, you multiply that together divided by 8, that tells you exactly how much memory it's going to be because it's a 2-color screen. It's very simple. Each bit is a pixel. P modes 1 and 2 take up 3K. One of them is 128 by 96 with 4 colors. So every pixel every pixel takes 2 bits, so there's 4 per byte, and that's 3K, or 128 by 92 with 2 colors, where every pixel takes 1 bit, so you can have 8. So it takes the same amount of space, but you have half as many colors when you go to the 4-color mode. And then P modes 3 and 4, 128 by 192 with 4 colors, or 256 by 192 with 1 color, both taking up 6K. And organizing them by pixels per byte, this is the important part. P modes 0, 2, and 4 are all 2-color modes, where each pixel represents 1 bit, so you get 8 pixels per byte, 1.5K, 3K, or 6K. And then P mode 1 and 3 are the 4-color modes with different resolutions, 128 by 96 or 128 by 192. Takes 2 bits per pixel, so you can get 4 pixels per byte in 3 or 6K. Now, my get and put discussion so far only applies to P modes 0, 2, and 4 because all my math assumes that every byte is going to hold 8 pixels. So when I did all my calculations and I said, oh, let's see, if the width is 32 and the height is 32, I would say print the number of pixels equals width type height. And that prints the number of pixels. And then if I wanted to see how many bytes does that take, I took pixels divided by 8, and then that needs 128 bytes of storage. Well, that only works if each byte is 1 pixel, because I'm doing the math right there. B equals pixels divided by 8. Obviously, if I was on P mode 3, the B would have been pixels divided by 4, I think. Is that right? Something like that. I'll get back to that in a minute. Basically, it's how many pixels fit in each byte. Yeah, I think that would be B equals pixels divided by 4, and then you end up with bytes of 256. So we're going to look at this in just a moment. That is probably, that's double. Okay, that's fine. 2 colors, 4 colors, 2 colors, 4 colors, twice as much. Okay, that works. Now, the reason this is important is because of how the data is stored. That's what get and put needs to know. You need to know how much memory your 16-pixel graphic is. If it's one of these modes, 16 pixels fits in 2 bytes. If it's one of these modes, 16 pixels doubles that size because you can only store half as many pixels per byte. To understand this, here's a quick demonstration. Let's look at the memory map of the color computer. Starting at memory location 0, the first 1K of RAM is used by Color Basic. It's the buffer you type in for typing in a basic program. It's pointers to where basic starts and ends, variable pointers, all kinds of stuff. And then at location 1024 at 1K, there's half a K for this beautiful green text screen. And then after the text screen, if you were on a cassette-based system, that's where these high-res graphics would start. If you weren't using them, that's where your basic program could start. Except BASIC won't let you actually start there. It always wants to reserve at least 1 page of graphics, whether you're using them or not. And there's pokes you can do to get around that and get all your memory. But on a disk-basic system, there is another 2K reserved right after the text screen for disk basic, for file buffers, and all kinds of stuff. So in my example, the high-res graphics are going to start at 3584. And why this is important? Well, I can poke at the first character of the text screen. I can poke a character there, and it appears on the screen. We can also poke onto the graphic screen. I'm going to start out by saying, let's make a new program, pmode 0, comma 1, clear the screen, screen 1, comma 1, 999, go to 999. Well, I can do a loop for I equals memory location 3584 to, let's just call it 3700. 30, poke I, comma 255, 40, next I. So this is going to start at memory location 3584, which is the high-res graphics screen, and it's just going to start poking 255. And that is a byte with all 8 bits set. So each poke will set 8 pixels. Let's see if it works. There it goes. Now, if I know how big this screen is, let's go back and look. A pmode 0, right here, a pmode 0 is 1.5K, 1536. So if I change this to 3584 plus 1536, we have to subtract 1 so it doesn't walk off the end of our screen. I now have a very slow way to paint the screen to solid all pixels on. And hopefully I don't go too far and crash my basic program. Looks like we're still good. Okay, so this is important because this will demonstrate how these pixels work. If I wanted to do a pattern like this, 1 0 1 0 1 0 1 0, I'd have to figure out what these pixels mean, what each bit is to turn it into a pixel. And the way a byte works is starting at the left, the first one is 1, then 2, then 4, then 8, and so on. So I happen to know that's 128 in the left column right there. Then that's 64. Here, let me just write them out. 28, 64, 32, 16. Do a next line. 128, 64, 32, 16, 8, 4, 2, 1. If you read these vertically, these are how those bits are stored. So if I wanted to do 1 0 1 0 1 0 1 0, it'd be 128 plus. The next one is 32 plus. The next one is 8 plus. The next one is 2. This value of 170. So if I just put 170 there, every other pixel. All right, so we can poke on the screen, and this gives us some interesting information. Now, since this is 1 bit per pixel in this mode, 1 0 1 0 1 0 1 0, that should give us 4 pixels. Or sorry, it should give us all 8 pixels, 4 on, 4 off. But if I change the mode and I want the same resolution, 128 by 196, let's go to pmode 1. It's the same amount of memory, or sorry, it's the same resolution, but it takes twice as much memory because now this 1 0 1 0 1 0 1 0 doesn't represent 8 pixels. It represents pixel 1, 2, 3, 4. And every 2 bits is a pixel. The pixel can be both off. It can be 1, 2, 3. There's your 4 combinations. In fact, let me make this so we can actually see this a little easier. I'm going to get rid of the loop. In 20, I'm going to poke 3584, comma 170. So if you look at this, there's 1, 2, 3, 4, 5, 6, 7, 8. This is the 0 over there. So I can actually see my 8 pixels. But as soon as I change this from pmode 0, 128 by 96, to pmode 1, 128 by 96, what do we see? Well, I can't tell. I certainly do not see pixel off, pixel off, pixel off. I just see solid pixels. That's because now 1, 0, 1, 0, 1, 0, 1, 0 isn't representing 8 individual pixels. It's representing this color, next to this color, next to this color, next to this color. So that is 4 pixels on the screen that are all the same color, whatever color 1, 0 is in binary. So now that is a byte, but it only represents 4 pixels. How can we tell? Well, let's see. If this was going to be on and off, and this was 1 pixel on, 1 pixel off, 1 pixel on, 1 pixel off, we could try to come up with the number that does the same thing. And we know that this was 1, 2, 4, 8 plus, and this was 128, so 128 plus 8, 136. 136. So line 30, poke 3584, comma 136, comment out line 20. I do that, and there are pixel on, pixel off, pixel on, pixel off. By changing the bit pattern now, I can get my 4 pixels. So 1 byte is 4 pixels in this mode. In a 2-color mode, 1 byte is 8 pixels. This means if I was calculating, say I knew I had an object that was 64 pixels across the screen, and I knew there were 8 pixels per byte, I would divide it by 8, and I would know it would take 8 bytes to represent 64 pixels. But if there were only 4 pixels per 4 bits per pixel instead of 8, or rather, whatever, I would divide this by 4. And now you see it takes twice as much room, because in the first example, I'm dividing it by how many pixels fit in a byte. That's 8. If it's a 2-color mode, 4 pixels fit in a byte. So it takes 16, twice as much memory to represent the same stuff. This is important because of how get and put work with the buffer. So let's do a quick example with that. If I start with line 10, and we're going to say x equals 0, y equals 0, width equals 32, height equals 32. We're going to kind of use that same example before, but we're going to make it simple, and we'll go ahead and delete 20 and 30. Typing is hard. Line 20, we're just going to do a line from x and y to x plus width minus 1 to y plus height minus 1, comma p set, comma b. So we're just going to draw that box. In p mode 0, I can figure out how much I need to dimension to hold it in a get by saying pixels equals width times height. The number of bytes equals pixels divided by 8. And then I did my formula to put it in an array. I said dim, my box is going to be, oh, actually, let's see, how many array entries? Well, the entries are bytes divided by 5, because each array entry gives me 5 bytes of storage. That's something we worked out in the previous example. Add plus 5. Actually, let me go ahead and make this an int to round that off. Line 60, print width height, comma, pixels, bytes, e. And if I run this, over here, 32 by 32, 1024 pixels, 128 bytes, 26 array entries of storage, line 70, comment that out, 70, dimension, box, e minus 1, that gives me 0 through 25, 80, get x comma y, dash x plus width minus 1, y plus height minus 1, comma, into the bx variable. If I run, this should work without an error, and it does. Line 90, we're going to put at, say, 32, comma 32, and we're going to go to 32 plus width minus 1, comma, 32 plus height minus 1, comma, bx. There we go. So that looks okay. However, if I change this to p mode 1, which is the same resolution, 128 by 96, let's look at it up here. I went from p mode to p mode 1, right here. but it takes twice as much memory. If I try to run this, it works, but why? Well, because everything is being scaled. I'm still giving it 32 by 32, even though on the screen it's actually being converted to half that resolution. This 128 by 96 still gives me coordinates that are 256 by 192. So what's going on is, while I am saying 32 by 32, this graphics mode is really 16 by 16. So this math I did based on pixels, it's going to work because I'm not really doing a 32 by 32 resolution graphic. I'm doing a 16 by 16. Out of curiosity, let's see what happens. Line 71, dimension bx should be 25. That works. 24. Still works. Guess what? I was wasting a lot of space because I calculated it based on virtual resolution. I said, oh, this is 32 by 32, but it's not. In this mode, it's really 16 by 16. So what I would have needed to calculate it was 16 by 16, 256 pixels divided by 8 bits per pixel, and then 32 divided by 5 per array entry would have been 7. So 0 to 6 would have been 7. So I think this will work in this mode. Ah, but wait. It doesn't. Am I off by 1? Well, it looks like there's something else going on here. Let's go back to P mode 0. Oh, wait, it works just fine. Why? Because the resolution is the same, but the one with the 4 colors is actually using twice as much memory. So if I am in the single color mode, my formula works. Width times height, in this case, the true number of pixels, 16 by 16, 256 divided by 8 bits per pixel gives me 32. 32 divided by 5 bytes per array entry, and you add 1 to that, so it's actually 7. So dimension of 6, 0 through 6. The moment I switch it to this mode, well, I'm giving it 16 by 16, the real number of pixels, but it's not 8 pixels per byte, it's 4. So I would have done the math that way. That says this takes up 64 bytes, 64 divided by 5 bytes per array entry, that's 12.8, that would be 13. I believe if I just put in 12, that should work in this color mode. So we double it, doubling it, and that works. 11 does not work. So this formula that I came up with in the get put video only works for 8 pixels per byte graphics modes. In other words, it will only work on modes P mode 0, 2, and 4, but not 1 and 3. So we need to do a little bit more work. We need to know if we're in modes 1 or 3. And if we're in 1 or 3, those are the modes that have 4 colors, and we divide by 4. And an interesting thing about this, you're going to notice that the ones that are 2 colors are 0, 2, and 4. The ones that are 4 colors are 1 and 3. And look at this pattern. In binary, here's 1, here's 0, here's 1, here's 2, here's 3. Notice that the 1 over here on this right column, that makes it an odd number. Well, since P mode 1 and 3, and then 4 would be like that. It'd be 3 bits. All I need to do, really, is if that bit is set, then I know that it's the P mode 1 or 3. So you could do a formula like this where you also wanted to know what P mode you were in. Like, let's do this as an example. Maybe I'm going to add line 0, P mode equals 0. So here I'm going to say, actually I'll just say M for mode. How about that? We'll call it mode. So which mode are we going to be in? So M is the mode. Then I'm going to say p mode 0, comma 1. Then when I do my calculations down here, line 40, bytes equals pixels divided by 8. Well, now what I need to figure out is, how do I know if I'm dividing by 8 or by 4? And there's some easy things you can do. For instance, all I could do is AND with 1. For instance, if I print p mode 3 and 1, I get 1. If I print p mode 4 and 1, I get 0. So if I AND the mode with 1 and it's even, I get 0. So one way I could do this, maybe, let's see if this works, is I could say divided by 8 minus, and then I will put in 4 times whatever the mode is and 1. So if the mode is 0, 2, or 4, it comes back 0, so it says 8 minus 4 times 0. That's 8. If it comes back with 1 or 3, then this will be a 1, so it'll be 8 minus 4 times 1. That's one way to do it. Let's see if it works. I will get rid of my line 71. I will put line 70 back. Run it with p mode 0. That works. Run it with p mode 1. That works. Well, that seems like a good idea. Let's run it with p mode 4. That works. Now the problem with this, remember, it's basing width and height on 256 by 192 no matter what. Even though in p mode 0, it's really 16 by 16. So again, this is not right. So there's two things we have to do. When we're calculating the number of pixels, pixels is width times height, that needs to be either 128 by 96 or 128 by 192 or 256 by 192. So we actually do need to know what the resolution is, and you can't easily get that from knowing whether or not it's even or odd, because I've got 0, which is 128 by 96, and 2 and 4. So if you look at how the memory is, we've got 3 conditions. If it's 0, you know it's the mode that's 16 by 16. If it's here, you're still this mode that's 16 by 16. But over here, that's something else, because the resolution is double the other direction. Of course, you already know it's 8 bits per pixel, so it really doesn't matter. But you need to know the resolution. 8 bits per pixel, 32 by 32, or 8 bits per pixel, 16 by 16 on the screen. So there's more math that needs to be done. I will do another part, and we will work that out. We'll come up with a universal formula for taking your P mode and determining how much memory it needs, and then we'll find out why that will still not work for everything. Until next time, don't panic.